Welcome to Chapter 5, Section 6, Taylor's Theorem. This episode is the payoff of everything we have built in this chapter. In Section 1, we define the derivative. In Section 2, we proved the mean value theorems. And in the previous episode, we climbed the tower of higher order derivatives, f prime, f double prime, and so on up to the derivative of order n. Today, all of that machinery comes together in a single result, Theorem 5.15, known as Taylor's theorem. It says that a function with n derivatives can be approximated by a polynomial of degree n minus 1, and crucially, it tells us exactly what the error of that approximation looks like. It is one of the most useful theorems in all of analysis. Let's dive in. Here is the plan for this episode. We start with motivation. We revisit the mean value theorem and see how Taylor's theorem grows out of it as a natural upgrade, replacing constants by polynomials. We then introduce the star of the show, the Taylor polynomial, and understand the sense in which it is the best polynomial approximation to f at a point. With the polynomial in hand, we state Theorem 5.15. Look at its special case and see how it lets us estimate errors in practice. The heart of the episode is the proof, a beautiful cascade of mean value theorem applications. Finally, we summarize and preview the last section of this chapter. Let's start from something we already know. The slide shows the mean value theorem, Theorem 5.10, rewritten in a suggestive way. F of beta equals f of alpha plus f prime of x times beta minus alpha for some x between the 2 points. The labels under the braces spell out the new reading. F of alpha is a constant approximation to f near alpha, and the second term is an exact error term, the first derivative at some intermediate point times beta minus alpha. A crude approximation, but with a perfectly precise error formula. That precision is what we want to keep. Now suppose f has not just one derivative, but n of them, as in the tower from the previous episode. Then approximating by a constant is wasteful. We are ignoring almost everything we know about f at alpha. The second bullet states the natural upgrade. Use all the derivatives up to order n minus 1 to build a polynomial of degree n minus 1 that imitates f near alpha as closely as possible. The question is whether we can still say something exact about the error. And here is the remarkable answer, the content of Taylor's theorem. When we pass from the constant approximation to the polynomial of degree n minus 1, the error term keeps exactly the same shape as in the mean value theorem. It is the derivative of order n, evaluated at a single unknown point, x between alpha and beta, divided by n factorial times beta minus alpha, raised to the power n. One derivative, one mystery point, one clean formula. Before we make this precise, let's see with our own eyes how good these polynomial approximations are. Here is the phenomenon in a picture. The dark teal curve is the sine function, which we take for granted as in example 5.6. Its rigorous treatment comes in Chapter 8. The red dot marks the point alpha equals 0, where we collect our information. The blue straight line is the degree 1 approximation, the tangent line, t itself. It hugs the curve near 0, but peels away quickly. The green curve is the degree 3 approximation, t minus t cubed over 6. Look how much longer it stays glued to the sine curve, following it well past 1 on each side. Both polynomials were built using only derivatives of f at the single red point. More derivatives, better approximation, and Taylor's theorem will tell us precisely how good. Let's set up the exact hypotheses. Here are the standing hypotheses. Notice that Rudin asks for exactly what the proof will need, and not a drop more. First, f is a real function on the closed interval from a to b, and n is a positive integer. Second, the derivative of order n minus 1 exists and is continuous on the whole closed interval, endpoints included. Third, the derivative of order n is required to exist only at interior points, and nothing is said about its continuity. Recall from the previous episode that this already forces all the lower floors of the tower of derivatives to behave well. Next, we introduce the two special points. Finally, we fix two distinct points, alpha and beta, in the interval. Think of them as playing different roles. Alpha is the center of expansion, the place where we know everything, namely the values of f and its derivatives up to order n minus 1. Beta is the target, the place where we want to predict the value of a f. Note that the theorem does not care which of the two is larger. Alpha can lie to the left or to the right of beta. With the cast assembled, we can now build the polynomial. Equation 23 defines the Taylor polynomial p. It is a sum over k from 0 to n minus 1, and the term of index k is the derivative of order k of f at alpha divided by k factorial times t minus alpha raised to the power k. Below the block, the sum is written out term by term. The constant term is f of alpha. The linear term is f prime of alpha times d minus alpha, then the second derivative over 2 factorial times the square, and so on. The first two terms alone give the tangent line. So p starts from the familiar linear approximation and keeps refining it. Notice that p is a polynomial of degree at most n minus 1, and it is completely determined by data at the single point alpha. Why these particular coefficients? The next slide gives the answer. Here's the sense in which p is the best possible choice. The gray box says that the derivative of order k of p at alpha equals the derivative of order k of f at alpha for every k from 0 up to n minus 1. In words, p has the same value as f at alpha, the same first derivative, the same second derivative, all the way up to order n minus 1. The reason is the little computation below the box. Take a single building block, t minus alpha to the power j over j factorial, and differentiate it k times at alpha. If j equals k, you get exactly 1. Otherwise, you get 0, because either a positive power of t minus alpha survives, or the term has been differentiated away entirely. So each coefficient of p is tuned to match exactly one derivative of f, and no coefficient interferes with the others. This matching property is precisely what the proof will exploit. Now for the theorem itself. Here it is, Theorem 515, Taylor's theorem. Under the hypotheses we fixed, there exists a point x strictly between alpha and beta, such that equation 24 holds. F of beta equals p of beta, the polynomial prediction, plus the derivative of order n at x, divided by n factorial, times beta minus alpha to the power n. Pause on how strong this is. It is not an approximate statement. It is an exact identity. All the messiness of the unknown function f is compressed into the single unknown point x. We do not know where x is, only that it lies between alpha and beta. But that is exactly the same kind of information the mean value theorem gives. In fact, Let's check that the mean value theorem is literally the simplest case of this result. Set n equal to 1 and watch the theorem collapse into an old friend. The sum in equation 23 then has only the term with k equal to 0, so the polynomial p is just the constant f of alpha. The hypotheses ask that f itself be continuous on the closed interval and differentiable inside, and equation 24 says f of beta equals f of alpha plus f prime of x times beta minus alpha. That is word for word the mean value theorem, Theorem 5.10, in the rewritten form we saw in the motivation. So Taylor's theorem is not some exotic new principle. It is the mean value theorem of order n, and the mean value theorem is Taylor's theorem of order 1. This also hints at the proof strategy. If the case n equals 1 is the mean value theorem, perhaps the general case follows by applying the mean value theorem n times. It does. But first, let's see why the theorem is so useful in practice. We never learn where the mystery point x is, and remarkably, we almost never need to. The gray box shows the standard way the theorem is used. Suppose we know a bound. The absolute value of the derivative of order n is at most m everywhere between alpha and beta. Since x lies in that range, equation 24 immediately gives the estimate on the slide. The error of the polynomial approximation is at most m over n factorial times the distance from alpha to beta raised to the power n. This turns Taylor's theorem into a computational tool. As the first bullet says, we can compute values of a complicated function to any desired accuracy from finitely many derivatives at one point. This is essentially how tables of sines and exponentials were computed for centuries. And as the second bullet notes, the n factorial in the denominator grows extremely fast, so the bounds improve dramatically as n increases. Now, let's prove the theorem. Before the formal argument, here is the plan of attack in 4 steps. Step 1. Instead of hunting for x directly, we define m to be the number that makes the conclusion true by brute force. The actual error at beta certainly equals some multiple of beta minus alpha to the an, so we let m be that multiple. The whole burden then shifts to showing that n factorial times m is a value of the derivative of order n. Step 2. We package everything into one auxiliary function g, the difference between f and its polynomial prediction, corrected by the m term. Step 3. The goal becomes simply that the derivative of order n of g vanishes somewhere. And step 4. The function g is designed to vanish so many times that repeated applications of the mean value theorem force a 0 all the way up at the level of the derivative of order n. This 2-part trick, an auxiliary function plus an iterated mean value theorem, is a pattern worth remembering. Let's carry it out. Step 1. Equation 25 defines the number m. Since alpha and beta are distinct, beta minus alpha to the power n is not 0, so there is exactly one number m, making the equation true. M is simply the actual error of the polynomial approximation at beta, rescaled. At this point, equation 25 contains no information at all. It is just a definition. The content of the theorem is the claim at the bottom of the slide. Nen factorial times m equals the derivative of order n of f at some point x between alpha and beta. If we prove that, then substituting back into 25 gives exactly equation 24. Equation 26 introduces the auxiliary function g. From f, we subtract the polynomial p and the correction term m times t minus alpha to the n. Note that g inherits the regularity of f. Subtracting a polynomial changes nothing about differentiability. Now let's see what the goal looks like in terms of g. Step 2. Differentiate the definition of g a full n times. The polynomial p has degree at most n minus 1, so after n differentiations it is wiped out completely. The correction term is m times t minus alpha to the power n, and differentiating that power n times leaves the constant n factorial. The result is equation 27. The derivative of order n of g equals the derivative of order of f minus n factorial times m at every interior point. Look what this does for us. If we can find a single point x between alpha and beta where the derivative of order n of g vanishes, then equation 27 says n factorial times m equals the derivative of order n of f at x, which is exactly what we need. So the entire theorem now rests on producing one zero of one derivative. The function g was engineered to make zeros plentiful, as we check next. Step 3. Let's count the zeros of g. At the point alpha, everything vanishes at once. Indeed, g is f minus p minus the correction term. The matching property from earlier says that p copies the derivatives of f at alpha up to order n minus 1. So in the difference they cancel, and the correction term t minus alpha to the power n vanishes to order n at alpha. It and its first n minus 1 derivatives are all zero there. The result is equation 28. G and its derivatives up to order n minus 1 all vanish at alpha. That is n separate pieces of information stacked at one point. At the other end, the choice of m in equation 25 was made precisely so that g of beta equals 0. That was the whole point of the definition. So g vanishes at both endpoints, and its derivatives vanish in bulk at alpha. Now the mean value theorem takes over. Step 4. The cascade. We begin with the function g itself. It vanishes at alpha, and it vanishes at beta. The mean value theorem applied between these 2 points produces a point x sub 1 strictly between them, at which the derivative g prime vanishes. In symbols, g prime of x sub 1 equals 0. This is the special case of the mean value theorem with equal endpoint values, often called Rolle's theorem. Between two zeros of a differentiable function, there is a zero of its derivative. One zero of g prime is found. But recall from equation 28 that g prime also vanishes at alpha, and that is exactly what lets us repeat the argument one floor up. Now we iterate, and the diagram shows the first 3 stages. Each horizontal line is a copy of the interval, labeled on the left by the function it belongs to. Green dots mark known zeros, and the red dot on each line is the new zero found by the mean value theorem. The top line records the step we just took, producing x sub 1. On the second line, g prime vanishes at alpha by equation 28 and at x sub 1. So between them there is a point x sub 2 where g double prime vanishes. The third line repeats the argument to produce x sub 3. At every stage, equation 28 supplies the fresh zero at alpha needed to continue. The stockpile of n zeros at alpha is spent 1 per stage, so the cascade runs for exactly n steps, ending with a point x sub n, where the derivative of order n of g vanishes. That is precisely the zero we were after. Let's assemble the conclusion. Each point produced by the cascade lies between alpha and the previous point. So all of them, in particular the last one, lie between alpha and beta. Call that last point x. The cascade tells us the derivative of order of g vanishes at x. Feeding this into equation 27, the derivative of order dn of f at x equals n factorial times m, and substituting this value of m back into the defining equation, 25 yields the boxed formula: f of beta equals p of beta plus the derivative of order n at x over n factorial times beta minus alpha to the power n. That is equation 24, and the proof is complete. Notice how economical it was. One cleverly chosen auxiliary function, and the mean value theorem applied n times. Let's step back and summarize the episode. Let's review what we learned. The headline is Theorem 5.50, Taylor's theorem. Under minimal hypotheses, continuity of the derivative of order n minus 1 on the closed interval and existence of the derivative of order n inside, the value of f at beta equals the Taylor polynomial built at alpha, evaluated at beta, plus an exact error term, the derivative of order n at some intermediate point x divided by n factorial times beta minus alpha to the power n. The polynomial copies all the derivatives of f at alpha up to order n minus 1, which is what makes it the natural choice. Second, perspective and practice. Setting n equal to 1 recovers the mean value theorem exactly, so Taylor's theorem deserves to be called the mean value theorem of order n, and although the point x is unknown, any bound m on the derivative of order n immediately converts equation 24 into a concrete error estimate. The polynomial approximates f to within m over n, factorial times the distance to the power n. This is the form in which Taylor's theorem is used throughout analysis and numerical computation. Third, remember the proof pattern. Define the auxiliary function g by subtracting from f both the polynomial and a correction term whose coefficient m is rigged to create a 0 at beta, then a cascade of n, mean value. Theorem applications pushes that 0 up the tower of derivatives, one floor at a time. This auxiliary function trick appears again and again in analysis, and several exercises of this chapter ask you to adapt it. In the next and final episode of Chapter 5, we ask what happens to differentiation when f takes values in the plane or in higher dimensional space. Some results survive unchanged, but surprisingly, the mean value theorem and L'Hopital's rule fail, and we will see explicit counterexamples together with the inequality that comes to the rescue. See you there.